Okay, so we just finished talking about the force of gravity, which we know was Sir Isaac Newton who figured it out. And today we're going to talk a bit more about him and the work that he did in figuring out all of forces. And he's probably most well known for his three laws of motion, which are what we're going to look at today. But before then, maybe I'll just do a little recap of this guy called Sir Isaac Newton. He was born in England in 1642. The Sir means he's a knight. He was knighted by the monarchy of his time, probably not long before he died, like after he figured everything out. So we know he did the universal law of gravitation. We know that he was able to persuade people into thinking that there were such things as non-contact forces, not just contact forces. But he's also the one who figured out what white light was made up of. Spoiler alert, when we get to waves, it's made up of all the other colors. And I'm not sure if you've seen the meme that's going around right now while we're in isolation, quarantine, but there's one that says something about, you think you're bored. How bored must Newton have been to invent calculus? So Newton is the person who invented calculus, not because he was bored, but because there were physics problems that he couldn't solve with the math that the math that they had at that time. So he created a new system of math, gave it to the mathematicians, and said, "Please teach this to students so that when we get them in physics, they'll know how to they'll be able to solve the physics problems." Okay. And of course, then the unit of force is also named after Newton. And we know that a Newton is equal to a kilogram meter per second squared, based on our Fg equals mg equation. Okay, and so originally it would have just been written, the units would have been written kilogram meter per second squared, but in time people got tired of writing it that way, and they recognized how much work Newton had done with forces, so they renamed it a Newton. Okay? So his three laws of motion. Now, I'm sure that you've heard of these. I'm absolutely positive you have. His first law is known as the Law of Inertia, and it says simply that an object at rest will stay at rest, and an object in motion will stay in motion unless an unbalanced force acts on it. An object at rest will stay at rest, and an object in motion stays in motion unless an unbalanced force acts on it. So right now, you and I are probably both sitting down. So we know the force of gravity is acting on us, because it always does. So it's pulling us downward, and whatever we're sitting on must be pushing up on us, because we're not moving. We're an object that's at rest, right? And so because we're at rest, there must not be an unbalanced force. So the chair or whatever you're sitting on must be pushing back with a force equal to the force of gravity. The same with your books on the table, right? Gravity is pulling them down, but the table must be pushing back with an equal force. There is no unbalanced force. It's also true with objects that are in motion. An object will stay in motion if there's no unbalanced force acting on it. So this ball will roll across the table because I give it a little nudge, and it'll keep rolling until an unbalanced force acts on it. It just ran into my computer, so it stopped. But if it hadn't run into my computer, and because there's not a lot of friction on a rolling ball, it would roll for quite a long while. If we took it to an ice surface that had been Zamboni'd and rolled it across that ice surface, it would continue to roll. So that's an object at rest, or an object in motion that will stay in motion unless an unbalanced forces act on it. Now, there's a couple of really interesting things connected to this. Think about when you're sitting in the passenger seat of a car, waiting for whoever to pull out. And so whoever it is late. So they jump in the driver's seat, they put the car into gear, and they step on the gas, and they zoom out. What is it that you do? What happens to your body? Now, most people would say that as the car pulls out, we're thrown back into the seat. But that is not what happens. So here's the seat, and here I am. Okay, I'm an object at rest, and I'm staying at rest. I'm just hanging out on this seat. But when the car goes forward, the back of the seat comes up and pushes me forward, so I start to move. But it feels like I'm thrown back into the seat, but it's really the seat pushing me forward. Now I'm traveling forward. Now the person slams on the brakes because they forgot their lunch. They slam on the brakes, so they're stopping, but I'm an object in motion and I'm staying in motion. And if I don't have my seatbelt on, then I'm not connected to the car, which the brakes are stopping, and I'm going to stay in motion until I run into the dash, until I hit the windshield, until I go through the windshield. It's why we wear seatbelts, right? So, because otherwise I'm an object in motion that stays in motion. Think about even going around a turn. When you go around a turn, when the car goes around a turn, you're traveling in a straight line, and the car curves, and so you keep traveling in a straight line until you hit the side of the car, which pushes you around the turn. Okay, so those are examples of objects in motion that stay in motion until they experience an unbalanced force. Another one is a space probe. We have a space probe that's on its way to the nearest star, which is like, I don't know how many light years away. Well, here's a news flash. There's no gas stations for it to stop at to refuel. So how the heck is it getting to this nearest star? Well, it's getting to this nearest star because we gave it a force, a big enough force to get it out of our gravitational pull of the Earth, and then it's just an object in motion that's staying in motion. There's no force acting on it in outer space, and so it's on its way to its nearest star. No fuel, no other force required. Okay? So those are objects in motion that want to stay in motion, or that are staying in motion, or objects in rest that are staying at rest. But what if we wanted that object to change motion? If I want that object to change motion, then I'm going to have to apply a force, right? I'm going to have to apply a force to get this person to stop. So I have to put a seatbelt on them. I'm going to have to apply, the seat applies a force to the body to move it forward. Okay, so when there is a change in what the object is doing, then it means a force must be applied to the object to create that change. And that's my second law. My second law is called the fundamental law of motion. And it says when an unbalanced force acts on an object, it accelerates that object in the direction of the force. That's really, the law really kind of ends there. It's just when an unbalanced force acts on an object, it accelerates that object in the direction of the force. And then the little footnote is the size of the acceleration depends upon the mass of the object. Well, that should make sense, right? If I put a force on this ball, I can make it move, it will accelerate. But if I put the same force on this textbook, it doesn't seem to do very much. And it's because the book has a much bigger mass. So there's an equation, and it's the second law that we use all the time when we're calculating. And the equation is F is equal to ma. And it's an unbalanced force. It's the net force. It's the total of all the forces acting on the body. Okay? So it's F net equals ma. And I usually write F net as sigma F equals ma. And I don't know if you've seen the sigma yet, but it simply means the sum. So let me make it bigger. So F net equals ma, which is the same as saying the sum of all the forces. So this symbol is a Greek letter, sigma, and it simply means the sum. And I write it because lots of times, like if we have an object that's pushing, has forces this way, and gravity, and is acting down, we'll do the sum of the forces in the x direction has to equal max, and the sum of the forces in the y direction